In this lecture, we're going to provide an introduction to the foundation of inferential statistics and review some of the procedures of sampling from populations. And so we start with an understanding of a population defined as the total collection of all cases that the researcher is interested in and wishes to understand better. So some examples might include all sociology students in Canada, all Canadians over the age of 65, all Canadians suffering from arthritis, or all people with cardiovascular disease. Now, access to every element or every person in a population is not very realistic. So from that, we obtain samples where we recruit and evaluate data from a much smaller subset of the larger population. Uh, and when we generate numbers that reflect the population, we refer to those numbers as parameters. And so in unique instances where we do have data generated from the population, we would describe those using Greek symbols, mu, sigma, and rho. So mu is the Greek letter indicating the average or the mean, and we'll make reference back to these symbols shortly. Lowercase Greek letter sigma is the symbol for the population standard deviation, and the symbol rho is it indicates a correlation coefficient that will be addressed in a subsequent unit. So in terms of the difference between a population and a sample, so just to review, we have the different symbols that represent a population parameter in the unique event that we have access to every element of the population and are able to generate data from every element. And if that were true, then the mean would be symbolized by mu. Sigma squared is the symbol for variance, and the square root of variance is the standard deviation. And at the population parameter level, we refer to that just simply as sigma. Now, if we obtain a sample, which is more likely the case, then we have different symbols. So X with a bar on top is what we use for the sample statistic of the average or the mean. The sample statistic symbol of S squared is the symbol for the sample variance, and the square root, just simply S, is the sample standard deviation. So the key aspect to understanding the difference between a population and a sample is that we wish to use the sample because it is accessible to researchers, and from our observations, we want to make judgments back to the population of interest. But we can't make a one-to-one, a perfectly certain conclusion, but our conclusions are based on the notion of probability, that the information generated, for example, between groups is statistically different. And this is what we'll expand upon in this unit, or a difference that would occur just simply by chance. And so on this lower illustration, here we have a population which could be all Canadians. And we want to know some information about all Canadians, but accessing every single person is not realistic. So from the population, we draw a random sample. And the rest of this lecture will talk about the different methods that are used to draw a sample. So the small sample, a very small subset of the population, is what we have to work with. From the sample, we make observations, we collect information, and we quantify the information as data, and we calculate various sample statistics. One example is X bar, which is the sample mean. And from the sample statistics, we then infer that the sample statistics are reflective of the population parameter mu, which is the population counterpart to X bar. So once again, X bar is the symbol used for the sample average, the small subset of the population, and we're going to use that and infer that it is a probabilistic reflection of the population parameter mu, which is the population average. Now, the different ways in which samples are drawn, we'll talk about the very first, the most simple way of doing this, and that's called simple random sampling. And conceptually, simple random sampling is an accurate representation of the population. This is not just with people, but this can occur with numbers. And so there is what's called a table of random numbers, where selecting a number from the table is based upon the fact that all the digits have an equal chance of selection. In doing so, there are two basic concepts with probability sampling and rather simple random sampling. The first is sampling with replacement. And this refers to that process where one unit is selected, it is added back to the population, and it has an equal chance of being selected again. And there are some instances, some research instances, where this is an appropriate way to sample. Most often, the sampling without replacement is often used in that after one unit is selected, it's no longer added back to the population, and it has no further chance of being selected. And this is something that occurs with lotteries, where numbers are randomly chosen, but when a single number is chosen, it's not added back into the lot. So that it will result in a series of unique numbers. Beyond simple random sampling, in most research studies, realistically, obtaining a sample has to follow some other systematic type of approach. And so systematic sampling involves a process in which the accessible population is first identified. Then the researchers determine what's called an interval size in order to begin the process of sampling from that population. And it's the interval size is the population size divided by the sample size, which is often determined prior to the process. The researchers would then select a number randomly between 0 and I, and that number is given the symbol of k, and then every kth person in each interval becomes the sample. And so if the interval size is, for example, 5.2, 5.2 is rounded to the nearest whole number, and that then a number is randomly selected between 0 and 5. If that random selection is a 3, then the third person in each interval becomes part of the sample. More systematic ways, more direct ways to obtain samples. The first is referred to as a stratified random sample, and this divides the population into subgroups. So for example, if we were interested in males and females or different university majors, we might approach this by obtaining what's called a proportional stratified sample. And this is a process which separates the population into different categories and then randomly selects a sample from each category. Now, the key thing with this, the key aspect of this process is that it is proportional. So the same relative number of samples will then be entered into each category. And so we'll use the example of SOM 3120, quantitative methods 1. And if we observe that we have a sample, or we have a total size of 300, there are 148 sociology majors, 97 anthropology majors, and 55 criminal justice and public policy majors. These numbers are fictitious. These are not actual numbers of student registrations in the course. But in designing a study, if we wish to obtain a sample from the students in the course, our goal would be to obtain 50% representation from each BA program. And so for sociology, that would amount to 74 students. Anthropology, we would round up to 49 students, and criminal justice and public policy, we would round up to 28 students. So these unequal absolute numbers indicate that this was a proportional sample, and they all represent half of each of the three major areas in the course. Now, the potential problem that is posed with this is that it becomes a statistical analysis issue. With unequal sample sizes, this can pose some potential problems with performing certain calculations. One way around that is to carry out what's called disproportional sampling. And that's often performed with different size populations with the idea of creating equal sample sizes. And so in this process, the same absolute number of samples are placed in respective categories. So let's go back to our same example. We have 300 students in the course with the same numbers as we saw in the previous example. Now, the goal here is to create a sample to put a total of 30 students in each group. And so we select 30 students from sociology, 30 students from anthropology, 30 students from criminal justice and public policy. So this would amount to a sampling of 20% of all the sociology students, 31% of all the anthropology students, and just slightly over half of all the criminal justice and public policy students would be in this sample. And the potential problem here is that criminal justice and public policy students might be overrepresented in comparison relatively to sociology students. And so we see here with proportional or disproportional sampling, there's no formula that would make one the correct way or the other. This would really boil down to the very specific research question that is posed. So we see both techniques offer potential issues, but there are remedies, at least statistically, to deal with those that we'll address later on in a subsequent unit. Another method to obtain samples is something called cluster sampling. And cluster sampling involves dividing a population of interest into subgroups or clusters according to specified criteria. Then a random selection of a pre-specified number of clusters is made. And then from those clusters, a pre-specified number of participants are then randomly selected. And so this is an image of the federal political ridings in the Toronto area. And so we see that the ridings are broken up based upon geographical location in Toronto, Humber Black Creek, Etobicoke Lakeshore, Beaches, East York, so on and so forth. With cluster sampling, a random the population in Toronto is already divided up into these pre-specified clusters, and then a researcher would then randomly select, not all of these, but randomly select a number of these pre-specified clusters, and then once that is obtained, then randomly select a pre-specified number of participants within each of those randomly selected clusters for telephone surveys to generate information on, in this example, political polling. The final type of sampling we'll address here is what's called non-probability sampling, and is one of the most common ways when dealing with human research participants. The first type is very commonly used and is a valid technique that is used, and that's referred to as a convenience sample. So this is obtaining a sample of research participants that is convenient to the researchers. And participants are based on availability. This does carry the bias of self-selection, but is one of the most popular methods that is used. So, for example, if a researcher at the university is conducting a study, they would obtain a convenience sample from from a group of students that are majoring in that particular area as a representation of all students. Quota sampling is another technique that's often used, and sampling and entering participants into a research study is usually stopped once an adequate number of participants is achieved. And this is another common way in which researchers can calculate a sample size based upon an expected outcome. And so, based upon previous studies and an expected outcome, there are methods to calculate how many participants a research study needs. Purposive sampling is a little bit more specific here, where much more specified criteria are established so that researchers can, quote unquote, handpick participants for that research study. And research studies involving human participants that require large sample sizes, such as administering questionnaires on attitudes towards educational methods at a university, then having a very large sample size is going to provide that study with a greater sense of validity. And so snowball sampling is one method that is incorporated, not the only method, but is often incorporated, where word of mouth or chain referral participants will inform other people that the study is taking place, and those people would contact the researchers for inclusion in the study. So this ends this part of our Unit 3 lecture.